and welcome to the podcast of Loughborough University's Institute of Advanced Studies, a podcast where our international fellows discuss the most pressing issues of today that we're all facing and share their exciting research ideas. We hope you enjoy today's talk. Thank you for tuning in. Hello and welcome everyone. I'm Professor Xenia Schmutz and I'm Director of the Institute of Advanced Studies. Welcome to the International House. It's great to see you in the room. Hello to everyone online. As always, we run this seminar as hybrid. It's really wonderful to have our fellow Ardila today. Thank you so much for joining us today. We're looking forward to learning about your research. Just a couple of housekeeping rules before we start. So as a hybrid seminar, we are recording, but it's only the presentation that will be released on YouTube and as a podcast. So, when we come to questions and answers, please feel free to comment, ask any questions. It will be great. For those of you in the room, of course, the discussion will continue over lunch after the presentation and the formal Q&A session. For those of you online, please post your questions in the thingy at the bottom, the box at the bottom. Still don't know what it's called after a year and a half. We are monitoring the questions. Well, without any further words from me, I'd like to pass to Anna, who's hosting our talk today.
Hello, yeah, it is my absolute pleasure to introduce Ardila. So we've met relatively recently as part of an enriched program, which is an Academy of Medical Sciences funded initiative that brings together researchers from Taiwan and Malaysia and Indonesia. And we've had a couple of successful meetings already so far, and this is an extension of that collaboration we hope that will last as a legacy beyond the project. So Ardila has a very long and travelled history. So she's originally from Indonesia and did her bachelor's and master's degree at the Institute of Technology in Surabaya? No.
Yes, it's
Surabaya, yeah, which is we visited very recently. She had been a process engineer at Chevron before doing her PhD at Taiwan Tech and continuing on then at Taiwan Tech as a postdoc and a project assistant professor, and finally took on assistant professorship at Taipei Tech, and she's now been promoted to associate professor relatively recently. So continuing her work there. But I will now hand over for you to talk about your very interesting and varied research.
Yeah. Thank you very much, Professor Anna, for kindly introducing me. This is very nice of you. And I would like to say thank you also for the IIS for welcoming me. This is very great journey. It was my first time I visit UK and then share with everybody. And thank you also for all of the audience here, to spend time to learn the research together with me. Yeah, so I think that today, I would like to bring it up, the issue of the CO2 capture, because here, as we know that every year the CO2 consumption, it was increasing, and we can feel also it's climate change is easily. So all it's because of the human activities. So we consume the fossil fuel and then even the airplane that somehow that I discuss about the CO2 capture, but I have to flew with the airplane. This is also consume one part, it's consume of the CO2. So we save our planet together. So I hope that we can extend some work together with the Loughborough University. It's my pleasure. So I'm Ardila. You can call me Ardila. I think it's easy. Yeah. So today I would like to discuss about the novel generations of the sorbents capable of the capturing carbon dioxide using the ionic liquids and also diphthitic solvents. I will focus on these two generations of the solvents because it's known, I think, in the chemistry, they try to develop some of the new green solvents, and it's easy to recover. So the first time that I would like to introduce a bit, so about Taiwan, it's quite far apart from UK. So I'm sorry, it's not reflects so here, it's the UK and Taiwan. Yeah, so it's around 16 hours by the flight. Yes, I hope that one day you can visit Taiwan. And this is our icon building, it's Taipei 101. Yeah, so it's exactly 101 floor. So if you visit the Taipei, so please kindly visit us. So Taipei Tech, it was the location, it was in the heart of Taiwan. So it's quite convenient to movable. So it's a type attack here. So which is center and then it's close to the airport and Taipei 101. So this is our first president. It's the President Chiang Kai-shek who found that democracy in Taiwan. Yeah. So in here that the history sums of my campus, like it start from the Japan at that time, historical of Japanese. 1912, it was Taiwan Public Taipei Industrial School. Then in 1948, they changed to Taiwan Provincial Taipei Industrial College. And 1984, then it's moving to the National Taipei Institute of Technology at 1997. Then it's become Taipei Tech. So this is our logo of the university. It's quite close. And they have the historical building. This building, it's indicate that it's already developed 100 years, more than 100 years ago. So it's just historical timbers. And then the outlines, it was, we will discuss about global carbon dioxide emission, challenge green solvents in industry, solubility carbon dioxide in green solvents, CO2 utilization. So after we capture, then what we're going to do about our capture. So we can use many types of the applications in industry, even they already apply, like supercritical carbon dioxide in the many applications in industry, and also some conclusions. So as you know that I think that all professors here and all of you know that the annual carbon dioxide emission, it was increasing. So I think the newest that I can get data, it was like 2023 and it's escalated up 2024. It's rising, is around 2 to 5%. So we can see that in here that it's contribute all, it's because of the fossil fuels. So we cannot even like give up from the fossil fuels because it was the mainly contributed. It's around like, even if we see that around 38 gigaton carbon dioxide already, like it's quite a lot of amount. And then what we can do in here that one way in the industry, and I think that a lot of the government's policy, like they try to capture, they try to apply one of the rules. I can see that zero carbon emissions. So they hope that industry can apply that, but I don't think that it will going to be zero because it's quite takes a lot of time. Even like we use the renewable energy, they still contribute on the carbon dioxide. So in here that decarbonization, it was one of the important technology. So once I found that about UK announced the new UK target to reduce emission by 81%. If we saw, we come back to the fossil fuel, even like the gas, they contribute is around 490 grams. Yes, I take from some of the information here, like the coal, they contribute the CO2, and then also like the nuclear offshore and the solar, but the amount of the CO2, it was quite minimum. So even in Taiwan government, they try to have the policy, it's about the carbon dioxide tax for the company. So all of the company now, they should reduce the consumptions. Either is used the pre-combustion, post-combustion or oxy-fuel. But today we will going to discuss about post-combustion capture because this is mostly happen in the applications. So they use currently amines in industry. To be honest, like it's quite a challenge for the academia to get the influence of or asking the industry, okay, you have to reduce the lemon consumption because it was the high volatile. However, in terms of the cost, they care about the cost of for the applications. And for the amine solvents, they have the weakness because the regenerations, takes a lot of cost. So then today, I will try to find some chemical sorbents, amine-based, but they still like, they have a low volatile vapor pressure because this is very important in the terms of the separation technology. Once we have the lower separation, lower vapor pressures, they can easily to separate the solvents and then from the CO2. So then we have the physical solvents like ionic liquids, biological buffer, and once the solvent, which this solvent, it will be helpful for industry to reduce the energy consumptions. Once we go to the chemical absorption, it will take a lot of energy and also cost for the separation process. So I think that about the green solvents in industry, the one that its criteria we would like to develop why it's green, it was non-volatile. We always claim it's non-volatile, but actually, indeed, we did have the vapor pressure, even it's very low. So today that I also would like to discuss about how we measure the vapor pressures in each of the green solvents that we synthesize and non-toxic. Now this is the one that we hope that all of the green solvent it should be non-toxic, non-flammability, biodegradability, renewable, stable is the most important. I think like once we synthesize or prepare of the solvent, it's quite challenging to get the stable and especially like how many times of the cycle for the green solvent and eco-friendly. So there is a sum of the ionic liquids and also the deep alkaline solvent we developed. One it was the ionic liquids and some of the typically conventional solvents to compare which one is better for the applications. And also we have the supercritical fluids. So these supercritical fluids, we call it this is as a green also. So normally we apply for the CO2, for the extraction process, for the drying, and then for so like lithium recycle battery, because in Taiwan, we develop a lot of a semiconductor field and then how to recycle them with the supercritical fluids, buffer aqueous solution, and also the deep alkatic solvents. So for the challenge that we face in the real, it was practically the green solvent, it's a good. However, for the solubility of the carbon dioxide, it's quite lower compared than the best of the conventional one as amine, and then also the recyclability because they care about how easy the green solvent or how many times the cycle that we can use, so they don't have to buy for the makeup solvents frequently, and also the costly chemical stability, highly viscosity. So normally, like in the CO2 capture, all the viscosity, highly density, it will hinder the CO2 solubility inside the green solvent. So we want to find the subsolvent, it's less viscosity and less density. So therefore, they can use for the applications, it's with the safe energy. They don't have to go to the high temperature for the capturing process and the scalability. Yeah. So this is the key. When we go to the scale up, from the scale down, go to the scale up, it will take a lot of considerations in terms of the cost. Also, this is the typically, and then also the stability of the solvents. So for this study, we would like to compare between organic solvent and the green solvent. So I think like green solvent, we always have the criteria about the low vapor pressures, and in this study, we would like to emphasize like how we characterize the solvent itself, vapor pressure determination, absorption or adsorption capability in the terms of the CO2 and reusability. So the first important in the characterization, I have to go back to the fundamental parts. When we say that it's vapor pressures, they always have the equilibrium between vapor and liquid. Yeah, so in here that the most important in the all properties, it should be reproducible. So if, doesn't matter we measure in the UK or in Taiwan, they have within the uncertainty, it should be equal or it should be similar. So we have many times of, it should be like time invariance, all flows is equal to B0 or no driving force, uniform, and map of the chemical reactions. Yeah, it should be equal. So all of this, we have to consider about uncertainty. I think this is nowadays, it's become like hot issue for industry. Most of the data, they don't consider about uncertainty, but uncertainty is very important in the application. First, the uncertainty, it's coming up from the measurement itself. So we have the thermometer, it can be used the mercury thermometer, thermocouple, RTD, this is all equipment. They have their own uncertainty. We should sum up, and also the pressure and the mole fraction. So for this is typically like 0.1 or 0.1%. It's from the equipment itself. Then another uncertainty, it's coming from the impurity of the chemicals. For example, we bought the chemicals from across already 99.9%, but it's not 100%. So that is also contribute of the uncertainty, and the thermostatic part or insulation, because they have the fluctuations during the measurements, and also if we apply some extra agitator. So all of this uncertainty, it should become like it should be summed up to characterize or to measure the properties of in the green solvents. So the first, like we use some example DES, but I think most of professors here and students, they know that how to synthesize or not synthesize, prepare of the deep alkatic solvent. It was the combination between two compounds. hydrogen bond acceptor and hydrogen bond donor. So one of the represents, we use dodecanoic acid and octanoic acid. Yeah, so this, why we choose this DS, the first, before we select the deep autotech solvent, we do the Cosmo to select and to see the energy, exactly energy interactions between your compound and then your DS. So more, less energy, or they are more negative, they are more favorable for the interaction. So in here that we can prepare some of the dodecanoic acids with the sum of the molar ratio. So in here I will use, for example, 1/2 molar ratio interactions. And then we can heat up until they are totally clear of the liquids. It's a bit viscous actually for the deep autotech solvents. So for here, like we can also play with the sum of the mixtures in terms, they can use another typically like some solvent to combine with the DS to reduce the viscosity or density. And then for the ionic liquids, I love this cation a lot because we try to reduce to use the amine. So this cation, it can combine with anything, anion, and to develop for the CO2 capture. So we use one of the example, it was protic ionic liquids here. So this is, we prepare some of the molar ratio, like 1:1 with the diisopropylethylammonium and propionic acid. And we did the typically like basic acid-base titrations and do the purifications. And we will check with the NMR, either they form the ionic liquids. And the second, we can use that one of the triazole-based ionic liquid. So this is quite new. I think like it's typically like it's not really new ionic liquids, but for the application of the CO2 is not done that much yet. So here that we prepare the 1,2,4 triazoles in the methanol and the sum solution we dropwise, and then we synthesize the tetraethyl ammonium 1,2,4 triazonium salt. Yeah, so these ionic liquids have to prepare in the 5 degrees C, and then we do the purification to remove the methanols. Check with the NMR, then I think that you can find the ionic liquids. So the first characterization, we check the degradability because this is the most important, that which area typically, like I think that's, it's they have something here that it was already like no even ionic liquids at 300 degrees C. It should be go to the spot here. So then if you compare that the DS, two of the DS in here, that it was that around 150 degrees C that they already like degradable, like not degradable, but they already decrease of the amount of the DS. So in here, like we can operate like lower than the 150 degrees C. So it's just to see that the characterization. And the other, it was the ionic liquids. I think I checked the sum of the ionic liquids. Yeah, it's around like 120. So means that our measurement cannot out of this thermal stability temperature. Then we check also with the density and viscosity. Sorry, this should be density. And then density with the temperature, when we increase, then it would be a little bit lower slightly. But if you compare with the conventional solvent, so actually like the DS is mostly, and the ionic liquid is quite, ionic liquid is lower, but the DS, it's quite a little bit higher compared than the MEA. Yeah? So it means that this is a big task if the industry or in the application we want to use this. So they have to consider to operate at a little bit higher temperature. This will be the problem in the absorber because they will stick inside the absorber column. So there we can see also from the viscosity, that from the viscosity we can observe that for the dodecanoic octanoic acid, it will be the mostly highest viscosity compared to the other solvents. Yeah, so in here that, I'm sorry, this should be viscosity. And then if we, before we do the experiments, that we check with the typically some of the conventional solvent to validate that its equipment, it's capable to measure our data or not. So we can see that some conventional solvent to compare, the first it was 1,2-propanediol and the other is CO2 and ethanol. So we can compare with the literature that we can see the trend or not, because like if we measure some of the solvent and the trend it was out of exactly, it's not similar, means that your equipment have some problem. So mostly the equipment in our lab, it was we assemble by ourselves and we combine together and to measure the vapor pressures or some VLE from the binary systems. So first, for the determination of the vapor pressures, we can use this equipment. So the first, we need the vacuum pump feed bottle. So this feed bottle, we can fill in with any kind of the green solvents and let it flow by the delta P. And then this equilibrium cell, we can control any temperature. So if you would like to measure the vapor pressures, we can use like even the lowest. We have the pressure transducer 100 millibar up to the highest one. So we can see that the pressure observation and verification, the composition analysis, either we want to check that is it any degradable in our component or not. So before and after we have to check our composition, it should be similar. Yeah, so in here, the first, it was degassing the equilibrium cell. So we want to remove, so the first, we can use the vacuum pump to remove any impurities inside the cell. Then we feeding the equilibrium cell with DS solution or any ionic liquids and control the temperatures and measure the vapor pressures inside the cell. So in here that we can see that the pressure record. Once we increase the temperature and then they will have the vapor compositions, it's following the Roche law because they are very low vapor pressures. This is what we claim that it's non-volatile, but actually there is volatile vapor pressures inside the deep atomic solvent or clean solvent. So the vapor is coming out because they have the kinetic energy, and then from the vapor, after increasing the temperature, and then they will detect it by the pressure record. Yeah, so until the pressure is stable for the recording, so we can sum it up. One example, this is cyclodextrin base, another type of the DES we try to measure. So here the cross symbol, right? It was the solid. Yeah, so it's very low vapor pressures. It's around 10⁻⁴. Then we the triangle blue one, it was the 1,2-propanediol. So the total vapor pressure, it was once they combine together, they have some interactions in the hydrogen bonding and the van der Waals interactions, and then it will become shrinkage. So the total vapor pressure is lower than their own conventional, their own individual component. Yeah, so this another also, we try to compare with another type of the DES and ionic liquids, and it showed that the ionic liquids also, and then the cyclodextrin, it was the lowest vapor pressure. So the highest, if we compare with the monoethanol amine, 38.59 kilopascal at 400 K. Yeah, so in here that we can confirm that the conventional one, yeah, this is what we want to reduce in the application. So we can replace with something like DS, even though based on the monoethanol amine, but the total vapor pressure is much lower. So if you see that the blue one, if we compare, yeah, we can see that it's almost like some percentage in here, like 10 kilopascal reduced. So here we can play with the sum molar ratio and also or to replace the ionic liquids if they are permissible for the CO2 capture. And we can try to measure also with the high pressure density method. So this is in extreme conditions, because before we use is only up to, we don't play with the pressure. Yeah, so in here that we can use this equipment to operate up to the 500 bar to see the properties of the green solvent. So in here, the process of this equipment, we have the vacuum pump here, and then we inject the green solvents, and once increase and then control the temperature, we can observe for the high pressure density. So this is one of example of the high pressure density. We also compare with the different types of the DES and ionic liquids. One is when we try to increase the pressure, the density is slightly increased. So in the flue gas, we don't operate at 1 bar. So in this case, that it will be helpful to see the properties. Like for example, like in the flue gas, we see that the CO2 capture is up to 20 bar. So here that once we increase, we have to have the slightly also considerations about viscosity and density. However, the viscosity for the high pressure is not that much effect a lot because it's just based on the vibration. So it's different with the density. For the oscillation, they will affect for the high pressures. So once we try for the applications, after we select some of the CO2 capture, the case study, second one, we try to measure the green solvent absorption capacity in the CO2 capture. So the equipment, we call it is phase equilibria analyzers. Inside the phase equilibria analyzer, you can see the transition of the phase, bubble point, critical points, or dew points. So since that we concern on the CO2 capture, it will be like bubble. It will be a very fast transitions that we would like to achieve. So this equipment, it can be operated up to 500 bar and 473.15 K. So the first, like the same, we would like to remove the some impurities inside the cell. Then once we inject it inside the cell of the R component, so in here that we can see that it starts with the single phase. So there is camera here that connected into to the monitor. So we can see exactly what happened phase behavior inside the cell. So once we reduce the cell, so we have the transition in here. One example, we have the bubble point, vapor liquid equilibria at 0.1006 mole fractions of the CO2. This is one of a DES example. So we can see that the carbon dioxide plus DES, the first, it was from the single phase. So it's nothing that we can see in the still homogeneous phase between the DES and the carbon dioxide. Once we reduce the pressure, we will have the vapor liquid transitions in here. So we can see that on the top of the cell, they have a single bubble, single stable, then we record it as the bubble pressures. So means that this DES, they're capable to absorb the 0.1006 mole fractions at the 0.77 megapascal or 7 bar. So this we can see that the capability of the solvents. If the pressure it's higher in the some specific of the solubility, means that the solvent is not quite good enough. So it's if you can capture the 0.1 mole fraction CO2, but you need the pressure it's quite lower, so it means that it's favorable. Because we don't want to have the high energy. Second, it was this application. It's for extractions. Normally for the DES to separation process, we can use some selection of the dew points. We can see it start from the homogeneous phase. When we decrease the pressures, we can observe the some liquid in the bottom of the cell. So when they start to change the phase from the vapor phase, go to the liquid phase, and then we can record it as a dew point pressures. So practically the transition, it's like this. So the black one on the bottom here, they start to have the liquid phase from the vapor phase. So it's typically the transition for the dew point. It's from the golden or from the black, and then they go to the start to have liquid in the bottom. And another, it was critical point. It was the interesting things, not only for the CO2 capture, but for the separation process. All of the data, it's a very limit, especially for the critical points. It's true that we can use the functional group to predict the critical points. But is it correct? So is it that we have to compare with the true in experimental parts, and we can see that the critical points means that at these conditions, we cannot see the distinguish of the phase. So we can see that when we decrease this one, it's totally like the vapor and the liquid, it was like half by half. So we cannot separate easily. So therefore, in the such kind of the phase equilibria, for the absorption methods, we can use the bubble points. And then for the extractions, we can use the dew points, except the critical points. So this is one of the phenomena that we found, that even in the DES, also we have the critical points. We can measure this in terms of the pure component or the binary component, or even you have ternary. So in here that we can see some mixtures or the pure components. So once we try to sum it up in here, that we have the calculations, because we use the high pressures. So Penrose-Robinson equation of states, it works well for this DES and then CO2. Once other representative in here, I use the thymol, octanoic, dodecanoic, octanoic as the representative. Then we can compare in here that once we use the typically dodecanoic, octanoic acids, if we see that comparisons, it's a bit lower compared than the thymol-based. So here that energy interactions of the dodecanoic acid is much more favorable compared than thymol. So even we can see the comparison at the fixed mole fractions of the CO2. The vapor pressure, the total pressure here, that it's much more lower. So it means that they are more favorable. So the open circle, it's for thymol octanoic, and then the open square, it's for the dodecanoic and octanoic acid. So if we compare with the other parts, it was have the ionic liquids, so and also the DES. If we see in here the monoethanol amine, that it was very favorite for industry. They always use this, of course, because they need lower energy compared than others, the green solvent. However, in here, because it's for the regeneration problem, we try to check either for the monoethanol amine choline chloride with the pure monoethanol amine, they have the good separation process or not. We can compare here, for example, like for the CO2, let's say for the MEA, it was 0.52 and the other it was 0.46. So we can compare in here like, and it the same pressure, you will get a solubility of the CO2 is much more lower for the DES compared to the conventional solvent. However, we can look it up. For the total vapor pressure, for the DES, it will be lower for the DES, means that they have advantage in the separation cost. So what's we going to do with this normally? We can use Aspen Plus or some engineering things to calculate typically the cost for the separations and the capture for the CO2. So from these simulations, we will get normally binary interactions parameter or BIPS to calculate the calculations of the cost in the CO2 capture technologies. We also try to compare if we try to increase the chain length of the ionic liquid, and we found that it was favorable use the short chains because the pressure here is much more lower at the same specific concentrations. And we use also biological buffers like EPPS, bysins. This is kind of the goods buffer. We use many typically in biological applications for this goods buffer. However, for the CO2 capture is quite unfavorable because here that we can see at the some specific concentration, the high pressure is required. So it means that it's consumed a lot of energy if we compare with the ionic liquids. We just need the 4.41, 44.1 bar, but we can capture around 0.5. So the loading is more than 1 already. So it's actually like, if we calculate based on the solubility, it's high. Then molecular dynamics simulation, CO2 with the ionic liquids is also confirmed that if we try to increase the chain length in the anion parts, in the ionic liquids, it was found that the shorter chains, they are more favorable compared to the higher chain length. So if you try to increase the chain length, then it will be, the solubility is become lower, because I think that the one things that we have to consider, it was the viscosity and density, that it was confirmed also from the characterization process. Then the third one, we try to use adsorption and frameworks, flexibility in the metal organic frameworks. So before it was absorption, and then we go to the adsorption. So this equipment, it can be used for the adsorber. So we can put some of the material here. You can use the metal organic frameworks or even the mesopores material. So inside, and then we can measure the capability of the CO2 by the gas chromatography by online. And this study we confirm also with RASPA simulations for the gas absorption flexibility for the CO2 capture. So this study, we can develop not only for the CO2 capture, but also you can use for the storage. Right now, like I think in Europe, they are trying to find some hydrogen storage to measure. So the first that we compare, it was, we synthesized the ZIF-8, one of the some pristine materials, and we encapsulate it with the ionic liquid. So we choose the best ionic liquid from the previous study and try to encapsulate it. And what we can learn in here, like for the lower vapor pressure, for the lower pressure, it was the ionic liquids encapsulation, it's give favorable compared than the high pressure. In the high pressures, the pristine ZIF-8, it will become better. If you can see that in here, for the encapsulations and for the ZIF-8, we try to study like different temperature, 303, and then also 318.15 Kelvin. So for this open square, it represents about the pristine Z8. For the circle, it was 5%, 5 mass percent. So we put the encapsulation. And for diamond, it was 10 mass percent, and we tried to encapsulate it with the highest 30 mass percent of the ionic liquids. And we can observe that below 20 bar, the trend, it was the 30%. Yeah, so it's much more give the favorable compared than the pristine. But once above the 20 run, so they will the pristine is much more better. So I think this phenomena, it's due to because when we encapsulate it with the ionic liquids, all the pores, it was like totally covered by the ionic liquid. So it somehow hindered typically the CO2 can go inside. So however this move, with the high pressure, they have the flexibility. So when we see that in the RASPA simulation, we can also confirm that when we did in the low pressures, so we can see that this is typically that how the CO2 goes. When we increase, then they try to typically that it's penetrate inside the metal organic frameworks. So somehow the flexibility and the pore size of the MOF, it will also some important factors to see that at the high pressures. If we compare that these simulations, I think it's quite close, even though here the red line, it cannot be totally like similar as the experimental results. So we try to see that what happened, the phenomena inside of this. So once in the low, I think that the CO2 particle is not that much. So to see that the typically where exactly position of CO2 fill in, the pore size inside the MOF, it's a big challenge for the experimental and simulation works. However, at high pressures, it's quite smooth and close with the experimental results. So once the study we can see from delta H absorptions. So once we see that in here, the pristine, it was the circle red color. And then with the ionic liquids encapsulation, it was the blue color. So when we compare in here that the ionic liquids encapsulation is give the favorable for delta H absorption. So that's because of the ionic liquids chain line, they can help also to absorb the CO2 in the systems. Yeah. So for these hydrate compositions, we will go to the CO2 utilization. How we use after we capture some of the technology, we said that it's have the CCUS. So carbon capture, utilization, and the storage. So there is actually applications that I don't put in here, I'm sorry, because the time limit. So they have hydrate carbon dioxide. So normally the hydrate carbon dioxide we can use to replace the methane. So once we want to explore the CH4, we have to replace with something inside the earth, inside in the exploration. So they use the CO2 to recycle back into the earth as the storage. And the second, for the CO2, we can use the DES, one of the application for the recycled lithium-ion batteries. So increasing of the electrical vehicle, especially in Taiwan, the one of the main sources that we use, it was semiconductor field. So one day the government will put the rules like company cannot only just sell, but also they have to deal with the recycle. So I think in some of the country, they already like also apply for that. And a large amount of the end of life lithium batteries will generated to be in the futures. There is a lot of issue for this because environment, shortage of the raw materials such as lithium, nickel, and cobalt. So I think this metal, one day, it will be famous. Yeah, so we have to think that how to recycle them back. So there is a lot of type method that possible to recycle, like pyrometallurgy, hydrometallurgy, and direct recycling. Yeah, so this is the most hope. Yeah, direct recycling is the best. However, to achieve that, it's quite difficult in terms of the purity. One of the case that in the company, they use the lithium batteries, they do the recycle or reuse. The problem, it was the lithium battery somehow goes fire by themselves. This is its cause because the purity is not that pure for the lithium battery. So they reuse perhaps the impurity still there. So once they apply in the lithium battery for the second cycle, it's happened. So this is like just know that we face also like electrical buses, they are burned by themselves. Yeah, so it's nothing effect because of the purity important. So here we have to consider about also like direct recycling, the regeneration, it's important, how pure it is. So the first, we can try to study about to screen the typically the solvent that we want to use for the recycling. I think this is currently under study. So the first we use, it was the ionization potential, because here that one of the screening is we can use the cyclic voltammetry to see that if you have the highest ionization potential, that it will be helpful for your deep acidic solvents. And also for the recycled battery, we can play with the temperature, of course, the pressures, and also your pH pattern. So in this case that we try to recycle, I get the spent battery from the company with some specific compositions, and we try to apply in the deep acidic solvent and observe the FeSEM after leaching. So we can see that in here that typically like all the lithium cobalt oxide, it was covered by the deep acidic solvents. We did before and after to confirm. And then after that, how the leakage after the extraction, it's separate from the deep acidic solvent or the green solvents. So most of that, we cannot only just taking care about how to extract, but also like how to reuse our solvent. So once we try to think about how to separate the metal from the deep acidic solvents, there is some ways they can use the third solvents, we call it oxalic acid. Yeah, so they can separate the metal from the inside DS. And the second, it was apply the supercritical carbon dioxide. So it's like supercritical anti-solvent to remove the metal ores inside the deep acidic solvents, and you can capture again. So we can observe like they have the some lithium. I just apply for the ZAM 0.1 grams of the lithium cobalt oxides inside the 10 milli of deep acidic solvent. That's why we get some small number as a representative. So for the supercritical anti-solvent, we can use to recycle for the DES. So we observe that the performance of the deep acidic solvent we use here, because acetic acid base, it's a good for the lithium for the pH lower pH. So we try to use the supercritical fluids. If we compare that the atmospheric normal pressure and the supercritical fluids, they have the high lithium extractions compared to the normal pressures. So in here it's promisable, because like when we try to apply for 1 hour, they are almost like 99% for the achievement of the lithium. And this is also confirmed with the cobalt extraction. So the cobalt, it was around 98. It's slightly a bit different with the cobalt extractions and lithium extractions. So we try to also cover with the nickel, but it's still on the study for the nickel. So we cannot only just focus on lithium and cobalt. So once in the spent battery, nickel, it also will be the future, how we recycle of the nickel problems. Then the another applications that we tried to use, it was to apply the supercritical CO2 for delignifications of the rice husk. So the biomass, I think in the Europe, we have a lot of bunch of the biomass availability. Then we can try to use to figure out how to apply the biomass waste into the some of the good materials or some of the profit material to reuse. So in here that we apply supercritical carbon dioxides, and then we calculate for the yield and products, and then regenerations of deep acidic solvents. For this study, we can cover two parts. One is soluble lignin inside the DS. The other part, it was insoluble lignin in the solid parts. So the one that I show here, it was insoluble lignin inside the rice husk. After the extraction, we still have some solid amount, and we try to measure that how much the lignin left inside that we can cover. So we can use that the high pressure equipment, and typically for this equipment, we use it's around 150 up to 170. Somehow that 120 depends on your DS. So we have to check TGA from the previously. So if they are degradable, it's around 120. You can operate up to 100. So normally for the extraction of the biomass, they need high temperature. So in the high temperature, we have to be careful with our solvents. Either at that conditions, our solvent will be degradable. So most of it was around 200 degrees C. But if we take a look from the TGA, at 200 degrees C, we cannot operate for the extraction biomass. So we have to operate before that. So how the solution we can combine with the some supercritical CO2 at high pressures, we can use other solvent, even supercritical water. So in Korea, they use supercritical water quite a lot. However, in the supercritical water, we have to concern that it's really high energy. So the critical of the water is around 374 degrees C. So it means that you have to operate up to above that. So once you combine with the green solvent, it will not work because the green solvent, it's around like, we can observe that DES or ionic liquids, we cannot achieve that high. So in this case that we try to see that how we can recover the lignin. So we see that in here that in the insoluble part, they have the cellulose content, hemicellulose and lignin, and also dissolve. So we try to confirm that from the raw materials and then up to 24. So once we see that lignins actually, it's only can be up to like 15%. So 4 hours, it's much more better because this is extraction. It was like, we cannot have typically the exact amount. So it should be like error bar there. So it's like plus minus. So if we compare that this one, inside of the rice husk, they have the hemicellulose, and the lignin. So lignin, when we try to measure, use the GCMS with the typically like a soluble lignin inside the DS, there is a lot of low aromatic hydrocarbon that we can achieve. And another, it was furfural. It depends on the conditions, extraction conditions, and you will get different type of the chemical. So means that green solvent, it works. Furfural, it's quite expensive. And somehow that I apply some condition, we can find GVL. So GVL, it's used as the entrainer. So it's for separating of the azeotropic mixtures. It's quite common in the applications. So we can apply for the bio-oil productions using the supercritical CO2. Then in here that I would like to conclude that from this study, we have the calibration, thermophysical properties. This is very important and missing. When we go to the literature data, it's quite difficult to find even the thermophysical properties, like the critical points, density and viscosity, especially at the high pressure. And solubility of the carbon dioxide in the deep autolytic solvent, green solvent, is very important. And we study about CO2 utilizations in the study case. And this number 5, it was for my students. So when we do the research, we have to be patient somehow that we have to recheck all the times, especially in the fundamental parts. We have to make sure that this data is accurate. So if your professor perhaps asking like, could you please recheck again, double check. So this is the most important part to see that data should be accurate. So I would like to say thank you to all the collaborators, especially to Professor Anna and all the professor here and student here that thank you very much for kindly giving time. And also that I would like to say thank you special for the Institute of the Advanced Studies. Thank you for your funding. And it's a great pleasure for me to be here. And I would like to thank you for your attention. If you would like to cooperate with Taiwan, we have several programs here, and feel free to contact me for the future cooperation. So I hope that it works. So we're currently working with Professor Anna. So all of faculty here is welcome to join us. And then I hope that my study in Taiwan can also support you to develop some of the new technology that is useful for the public and community. Thank you very much for your attention.
Thank you for listening to the podcast of Loughborough University's Institute of Advanced Studies. A quick reminder about how to stay connected. You can find us on Blue Sky, LinkedIn and Instagram, and you can also watch the presentations on YouTube. The podcast is available on all the major platforms. Please download, share, and most importantly, subscribe. See you next time.